Hello, welcome to my third speed-up video. Today I want to check out which hardware is required to increase the speed of generating a timetable with FET. So I just generate a timetable and check the task manager. As you can see, neither the graphics card nor the Ethernet nor the disk are used, so they have no impact on speed. The CPU is only partly used since it's a 4-core CPU. I will explain how to use all 4 cores in a later video. The memory is, of course, also used a little bit. So the speed should be affected by the CPU and the memory. Let's take a closer look. I wasn't able to change the clock speed of my Intel CPU, so I switched to my Raspberry Pi 4B. By default, it is running with 1.5 GHz and needs 4 minutes and 19 seconds to solve the dataset. I decreased the frequency to 0.5 GHz, but it wasn't 3 times as slow. It took 12 minutes and 35 seconds to solve. To understand it, we should think the other way around. If I increase the speed 3 times, why is it not 3 times faster? Shouldn't it be solved in 4 minutes 11? The speed of the memory is different from the speed of the CPU, and the cache is present in between. It may not be exactly 3 times faster or slower because of this. So, how much RAM is required by FET? Memory is required for both the data and the instructions. In the ideal scenario, neither is kept in memory, only in the cache. Let's calculate how much memory the data requires. My sample set requires 70.1 MB when opened in FET. It immediately consumes 74.7 MB after generating. 4.6 MB are therefore required for the data. To estimate the needed RAM for the instructions, I run FET in command line version. If it generates, it uses 16.6 MB, so 12 MB for instructions. Of course, this is not only used for the generating algorithm. There are also a lot of instructions for reading, preparing and exporting the data. The object file size is only 1 MB, but on the other hand, functions from the Qt shared libraries are also used, so I guess the needed RAM for instructions is around 2 MB. Therefore, a cache of no more than 8 MB in total could be ideal for producing a single dataset. I investigated the needed cache some more with a software called valgrind. The tool CacheGrind can simulate how a program interacts with the cache. For my old AMD CPU, I got the following results. It has 64 KB first level cache size for the instructions and also for the data. The last level cache, second level cache size is 1 MB per core. The first block is about the called instructions, the misses of the first level cache and the misses of the second level cache. There are misses in the second level cache, but they are below 0.01%. There are only some bigger misses in the first level cache. Since the Raspberry Pi has a smaller first level cache, there will be a higher miss rate. The second block is pretty the same, just about the data, not the instructions. Even though the miss rate with 1 MB second level cache size is already pretty low, I simulated different second level cache sizes, from a quarter megabyte to 256 MB. As you can see, the misses don't change anymore if the cache size is over 16 MB. The 180,000 misses are unavoidable, since the data don't exist in the cache if you access the first time, so I subtracted them on the right side. So far I must assume that the memory speed is not critical. To prove that, I generated the dataset once with the original clock frequency of 1600 MHz and once with a half frequency of 800 MHz. Even with the half clock frequency, I didn't measure a difference in time. Summing up. Of course, it depends on your dataset, but the generating speed mainly depends on your CPU and its cache size. The impact of memory speed is very small. If you don't want to miss a video about timetabling with multi-core CPUs, please subscribe to my channel. Have a nice day.